March 14, 1967. 2:47 p.m. Tan Son Nhut Air Base, South Vietnam. The UH-1 Huey sits on the tarmac. Rotors spinning. Engine humming. 6 soldiers strapped inside, boys from Ohio, Texas, California. They're headed to landing zone Albany. Extraction mission. Routine. The crew chief gives the thumbs up. The pilot pulls collective. The Huey lifts. 10 feet. 20. 30. Then a single bullet punches through the aluminum skin. It's a stray round. Maybe from a distant sniper. Maybe from celebratory fire 2 miles away. It doesn't matter. The bullet pierces the fuel cell, just below the main cabin. Just above the auxiliary tank. For 1 second, nothing happens. The fuel sloshes. Vaporizes. Mixes with oxygen in the tiny air gap inside the tank. Then the spark. The Huey doesn't explode like in the movies. No fireball, no dramatic slow-motion bloom. It detonates. Instantly. Completely. The fuel tank ruptures outward with a force of 200 pounds of TNT. Metal shreds. The cabin disintegrates. The tail boom separates. What was a helicopter becomes shrapnel. The 6 soldiers inside don't have time to scream. They don't have time to think. One moment they're airborne. The next, they're gone. The wreckage rains down across the runway. Burning. Smoking. A black scar on the concrete. Ground crews sprint toward the crash. But there's nothing to save. No survivors. No bodies intact enough to identify without dental records. Just fire. And silence. This is the 4th helicopter lost this week. The 12th this month. The 83rd this year. And it's only March. 7,000 miles away, in a small office at Wright-Patterson Air Force Base in Ohio, a man named Captain Robert H. Korkosz stares at a stack of crash reports. Each one tells the same story. Aircraft hit by small arms fire. Fuel tank punctured. Explosion. Total loss. The numbers are staggering. In 1966 alone, the U.S. military lost 441 helicopters in Vietnam. Not from missiles. Not from anti-aircraft guns. From bullets. Small caliber rounds that shouldn't be able to destroy an aircraft. But they do. Because of the fuel. Korkosz picks up the phone. His hand shakes. He's been investigating this problem for 8 months. He knows what's happening. He knows why these aircraft are exploding. And he knows how to stop it. But no one will listen. The solution sounds insane. Impossible. Childish, even. Fill the fuel tanks with foam. Like soap. Like a kitchen sponge. A material so light it floats on water. So porous it holds almost no weight. Something that shouldn't work. But it does. Korkosz has the test data. He's seen it with his own eyes. A fuel tank filled with reticulated polyurethane foam, shot with a tracer round, point blank, doesn't explode. It doesn't even ignite. The foam breaks up the vapor. Prevents combustion. Stops the chain reaction before it starts. It's so simple it sounds like a joke. And that's exactly why the generals won't approve it. You want to fill our fuel tanks with foam, they say. You want to add weight, reduce capacity, complicate maintenance, for a theory? Korkosz looks at the latest report. 1D. Tail number 66 to 16,823. Lost today. 6 dead. He thinks about the families. The letters. The flag-draped coffins. He picks up the phone again. This time, he's not asking permission. To understand why aircraft were exploding over Vietnam, you have to understand what happened inside a fuel tank when a bullet passed through. The answer is chemistry. And it's brutal. Aviation fuel, JP-4, the standard in the 1960s, is a kerosene-based mixture. It's volatile. High energy. It doesn't just burn. It evaporates. And those vapors are what kill. Here's what happens in the 3 milliseconds after a bullet penetrates a fuel tank. The projectile rips through the aluminum skin. Metal fragments scatter inward. The fuel sloshes violently from the shock wave. Some of it vaporizes instantly from the heat of the bullet, which is traveling at 2,800 feet per second. The vapor mixes with oxygen in the air gap at the top of the tank. This creates a combustible mixture, perfect stoichiometry, chemists call it. The ideal ratio of fuel to air. Then comes ignition. It can be the friction of the bullet, a spark from metal-on-metal contact, the heat from a tracer round. Sometimes it's static electricity. It doesn't matter. Once ignition occurs, the flame front propagates through the vapor at 1,500 feet per second. Pressure spikes. The tank ruptures. The aircraft disintegrates. Total elapsed time, 0.003 seconds. This wasn't a new problem. Aircraft had been exploding since World War I. The British lost hundreds of planes this way. So did the Germans. The Americans. Everyone. By World War II, engineers developed self-sealing fuel tanks, rubber layers that closed around bullet holes, preventing fuel from leaking. It helped. It saved lives. But it didn't stop explosions. Because the vapor was still there. Still combustible. Still waiting for a spark. In World War II, the solution was altitude. Bombers flew at 25,000 feet. Fighters stayed high and fast. Most aircraft could outrun ground fire or avoid it entirely. Vietnam changed everything. Helicopters flew low, slow, predictable. They hovered over landing zones, exposed, while soldiers jumped out. They followed the same routes, the same altitudes, the same approach angles. And the enemy knew it. The Viet Cong didn't need anti-aircraft guns. They used AK-47s, SKS rifles, even pistols. They fired upward, into the belly of the helicopters, where the fuel tanks sat. One bullet. That's all it took. In 1965, the U.S. lost 189 helicopters. In 1966, that number jumped to 441. By 1967, the rate was accelerating. Projections showed that if nothing changed, the military would lose over 600 helicopters that year. Each helicopter cost $250,000. Each crew, pilot, co-pilot, crew chief, gunner, represented years of training. Thousands of hours. Irreplaceable experience. And then there were the passengers. The infantrymen. The wounded being evacuated. The medics. The total killed in helicopter fuel tank explosions between 1965 and 1967, over 1,200 men. The Air Force knew it had a crisis. In September 1966, they formed a task force, the Fuel Tank Vulnerability Reduction Program. The mission: find a way to stop fuel tank explosions. Test every possible solution. Implement it immediately. They tried everything. Nitrogen inerting systems, pumping inert gas into the tank to displace oxygen. Too heavy. Too complex. Required constant maintenance. Explosion suppression systems, detecting the initial combustion and flooding the tank with halon gas. Too slow. The explosion happened faster than the system could react. Reinforced tank walls. Thicker aluminum. Kevlar liners. None of it mattered. The explosion came from inside. Strengthening the walls just made the bomb more effective. By early 1967, the program was failing. That's when Captain Robert Korkosz found the foam. He wasn't looking for it. He was reviewing old research files, studies from the 1950s that had been shelved and forgotten. One document caught his eye. It was a patent, filed in 1956 by a chemist named Robert A. Voles. The invention: reticulated polyurethane foam. An open-cell structure. 97% air. 3% solid material. It looked like a kitchen sponge. Felt like one too. Weighed almost nothing. Voles had invented it for air filters. The patent showed diagrams of industrial applications. Nothing about fuel tanks. Nothing about aircraft. But Korkosz saw something else. The foam structure, millions of tiny interconnected cells, would break up any vapor cloud, prevent it from forming a combustible mixture. The air could still flow through. The fuel could still flow through. But the vapor couldn't concentrate, couldn't reach the stoichiometric ratio needed for combustion. It was elegant, simple, brilliant. Korkosz ran the numbers. A fuel tank filled with reticulated foam would weigh only 3% more, would reduce fuel capacity by less than 2%, would require no power, no maintenance, no moving parts, and it might stop the explosions. He needed to test it. That simple idea was about to save hundreds of lives. But first, he had to convince the generals it wasn't insane. The breakthrough happens in the most mundane place imaginable. A hardware store. January 1967. Fairborn, Ohio. 3 miles from Wright-Patterson Air Force Base. Captain Korkosz walks down the aisle, past paint cans and screwdrivers, looking for something he can't quite name. He's thinking about Vol's patent, about the foam structure, about how to test the concept without requisitioning official materials, because official channels move slowly and men are dying daily. He stops in front of the cleaning supplies. There, on the bottom shelf, is a bag of polyurethane sponges. Kitchen sponges. Yellow. Rectangular. 99 cents for a pack of 6. He picks one up. Squeezes it. The cells compress, then spring back. He holds it up to the fluorescent light. Sees the structure. The interconnected pores. The open pathways. It's not reticulated foam. Not technically. The cells are closed, not open. But the principle is the same. He buys 12 packs. Back at the base, Korkosz walks into the workshop. It's after hours. The building is empty. He clears a workbench and spreads out his materials. 6 kitchen sponges. 1 metal container, a surplus fuel cell from an F-4 Phantom, salvaged from the scrapyard. 1 gallon of JP-4 aviation fuel. 1 M1911 pistol, loaded with tracer rounds. The test is simple. Dangerous. Probably against a dozen regulations. He doesn't care. First, the control test. He fills the empty fuel cell halfway with JP-4. Seals it. Carries it outside to the test range behind the workshop. Sets it on a concrete pad, 50 feet from the firing line. He aims. Fires. The tracer round punches through the aluminum. There's a flash, white hot, and then the fuel cell explodes. The shock wave rattles the windows behind him. Burning fuel splashes across the concrete. Black smoke rolls upward. Exactly what happens over Vietnam. Every day. He waits for the fire to burn out. 30 minutes. Then he retrieves the shredded remains of the fuel cell. The walls are blown outward. Petals of torn metal. The internal structure is gone. Now the real test. He takes a second fuel cell. This one, he fills with the kitchen sponges. He cuts them into strips, packs them tightly, filling every cubic inch of space. Then he pours in the JP-4. The fuel soaks into the sponges. Saturates them. The cell is just as full as before, but now the space is occupied. Structured. Divided into millions of tiny cells. He seals it. Carries it to the test pad. His hand is steady. His mind is racing. If this works, if this crazy idea actually works, it changes everything. If it doesn't, he's wasted 2 months and gone nowhere. He raises the pistol. Aims. The fuel cell sits on the concrete, gleaming in the January sun. He fires. The tracer round hits. Sparks fly. And then, nothing. No explosion. No fireball. No shockwave. The bullet hole smokes slightly. Fuel leaks out, dripping, not spraying. The sponges inside are burning. He can see a faint glow through the puncture, but the combustion is localized. Contained. It can't propagate. Can't build pressure. Can't detonate. Korkosz stares. He walks forward. Slowly. The fuel cell is intact. Dented. Punctured. but whole. He fires again. Same result. Burning, but no explosion. A third shot. A fourth. 5. 6. Every time, the fuel cell survives. His heart is pounding. His mind is spinning through the implications. If kitchen sponges can do this, if 99-cent cleaning supplies can stop a fuel tank from exploding, then proper reticulated foam, engineered for this exact purpose, could be the answer. He runs the calculations in his head. Weight, volume, cost, logistics. It's feasible. It's practical. It's something the military could actually implement. But there's a problem. He's a captain. Low ranking. No authority. And the solution sounds absurd. Fill fuel tanks with foam. It sounds like something a child would suggest. He needs proof. Real proof. Under controlled conditions. With official oversight. He needs to test it under fire. Literally. March 22, 1967. Wright-Patterson Air Force Base. Building 450. 9 a.m. The test chamber is 50 feet long. Reinforced concrete walls. Blast-proof observation window. Inside, 2 fuel tanks sit side by side on steel pedestals. They're identical. Surplus tanks from UH-1 helicopters. Each holds 40 gallons. Tank 1 is standard. Empty except for 30 gallons of JP4 and the vapor space above it. Tank 2 is packed with reticulated polyurethane foam, the real material, not kitchen sponges. Korkosz finally got approval to order it. Cost, $400. Weight, 4.2 pounds. It arrived 2 days ago. 15 people stand behind the observation window. Generals, colonels, engineers, civilian contractors. All of them skeptical. One of them is Brigadier General Marcus Hollis. He's in charge of the Vulnerability Reduction Program. He's lost patience with theories. He wants results. Captain Korkosz, Hollis says. His voice is flat. Tired. You're telling me this foam will prevent fuel tank explosions? Yes, sir. You're telling me it will stop tracer rounds, high-explosive incendiary rounds, armor-piercing rounds? Yes, sir. You're telling me we should retrofit every helicopter in the inventory, add weight, reduce fuel capacity, change maintenance protocols, all based on foam? Korkosz swallows. Yes, sir. Hollis stares at him, then at the tanks. All right, let's see it. The test begins. A remote-controlled rifle is aimed at Tank 1. Standard configuration. No foam. The baseline. The rifle fires. The sound is sharp. Contained. The bullet punches through the aluminum, visible through the observation window as a bright flash, and then the tank detonates. The explosion is instant. Violent. The tank splits apart, walls peeling back like a tin can. Flame blooms. Smoke billows. The pressure wave cracks the observation glass. A spiderweb fracture spreads across the center. Someone behind Korkosz curses. Another steps back. The fireball burns for 12 seconds before the suppression system activates. Halon gas floods the chamber. The flames die. When the smoke clears, Tank 1 is destroyed. Unrecognizable. Hollis doesn't react. He's seen this before. He's read the reports. This is what kills his pilots. Tank 2, he says. The wreckage is cleared. Tank 2 is positioned. Identical to Tank 1, except for the foam inside. The rifle aims. Fires. The bullet hits. Korkosz holds his breath. The tank remains intact. There's no explosion. No fireball. No shockwave. The bullet hole smokes. Fuel leaks, a thin stream, dripping down the side. Inside, through the puncture, a faint glow is visible. The foam is burning. Smoldering. But it can't spread. The combustion is localized. Trapped in the cells. Starved of oxygen. 10 seconds pass. 20. 30. The glow fades. The fire extinguishes itself. Tank 2 sits undamaged. The room is silent. Hollis steps forward. leans closer to the glass. Again. The rifle fires. Same tank. New hole. Same result. Smoke. No explosion. Again. Third shot. Fourth. Fifth. Each time, the tank survives. Each time, the foam contains the combustion. Prevents propagation. Stops the chain reaction. By the seventh shot, the tank is riddled with holes. Fuel is leaking from multiple punctures. But it's still structurally intact. Still functional. No explosion. Hollis turns to Korkosz. His expression is unreadable. How much does it cost? $400 per tank, sir. The foam itself. Installation is minimal. Standard maintenance crew, 30 minutes per aircraft. Weight. 4 pounds per tank. Fuel capacity reduced by 1.8%. Maintenance. None, sir. The foam is inert. Doesn't degrade. Doesn't require inspection. It's a one-time installation. Hollis nods slowly. He's doing the math. $400 per helicopter. The Air Force has 2,400 Hueys in Vietnam. That's $960,000. Less than the cost of 4 lost helicopters. And it could save hundreds of lives. What about fire? Someone asks. A colonel. If the foam is burning inside the tank. It self-extinguishes, Korkosz interrupts. The combustion consumes the available oxygen in the immediate cells. The fire can't spread to adjacent cells. It's isolated. Contained. The tank can still be refueled and flown. What if the tank is punctured multiple times? Same result. Each puncture creates a localized fire. None of them propagate. None of them detonate. Another question. What about impact? If the helicopter crashes, the foam compresses, absorbs impact energy. In some crash tests, it actually reduced structural damage. The questions continue. Logistics. Supply chain. Training. Compatibility with existing systems. Korkosz answers every one. He's been preparing for this moment for 3 months. He knows the data. He knows the specs. He knows the objections. Finally, Hollis raises his hand. Silence. How soon can we start installation? Korkosz blinks. Sir, how soon can we retrofit the fleet? If we order the foam today, 60 days for manufacturing. Another 30 for distribution. Installation can begin immediately after. Hollis looks at the shattered observation glass. At Tank 1's wreckage. At Tank 2, still standing. Do it, he says. No ceremony. No congratulations. Just 2 words. But in those 2 words, everything changes. The order goes out on March 24, 1967. All UH-1 helicopters in theater are to be retrofitted with reticulated polyurethane foam fuel tank systems. Priority, immediate. It should have been simple. It wasn't. The first resistance comes from the supply chain. The foam manufacturer, a small company in Michigan, has never received a military contract this large. They don't have the capacity. Don't have the raw materials. Don't have the workforce. We can deliver 500 units per month, they say. Maybe 700 if we add a second shift. The Air Force needs 2,400 units. Immediately. Find a way, Hollis tells them. The company hires 40 new workers. Leases a second factory. Runs 3 shifts. By May, they're producing 1,100 foam inserts per month. Still not enough. But it's progress. The second resistance comes from the field. Mechanics in Vietnam don't understand the foam. Don't trust it. They've been trained to keep fuel tanks clean. Empty. Free of contamination. Now they're being told to stuff them full of sponge material? It'll clog the fuel lines, one crew chief says. It'll trap water. Cause corrosion, says another. It'll add weight. Reduce performance. The complaints flood back to Wright-Patterson. Korkosz fields dozens of calls. Writes technical bulletins. Explains the chemistry. the physics, the test data. Most mechanics ignore him. But then something happens. May 7, 1967. Chu Lai Air Base, South Vietnam. A UH-1 lifts off for a supply run. Pilot, Chief Warrant Officer Daniel Reeves. It's his 147th mission. Routine. 3 minutes into the flight, the helicopter takes fire. An AK-47 burst from a tree line. 2 rounds hit the fuselage. 1 punches through the fuel cell. Reeves braces for the explosion. It doesn't come. The engine coughs, sputters. Fuel pressure drops. But the helicopter doesn't detonate, doesn't catch fire. Reeves brings it down. Hard landing. No injuries. When the ground crew inspects the fuel tank, they find the bullet hole. Find the foam inside, blackened, smoking slightly, but intact. The combustion was contained. Localized. The tank didn't rupture. Reeves walks away. His crew walks away. Because of the foam. Word spreads. Within a week, every pilot in the 1st Cavalry Division is asking about foam-filled tanks. Within 2 weeks, mechanics are installing it voluntarily, pulling foam inserts from other aircraft, retrofitting their own birds. The resistance evaporates. By June, installation is ahead of schedule. But there's a third problem. One Korkosz didn't anticipate. The enemy adapts. Viet Cong intelligence officers notice that helicopters aren't exploding as often. They don't know why, they don't know about the foam, but they see the pattern. So they change tactics. Instead of aiming for the fuel tanks, they target the engines, the rotors, the tail boom, areas where a hit still guarantees a kill. The overall loss rate doesn't drop as much as predicted. Instead of 600 helicopters lost in 1967, the final number is 542. Still devastating. Still unsustainable. But 58 helicopters that should have exploded didn't. 58 aircraft saved. At least 240 lives. Probably more, counting passengers. Korkosz reads the after-action reports. He knows the numbers. He knows it's not enough. But it's something. Then, in August, a letter arrives. Handwritten. Postmarked from Da Nang. Captain Korkosz. You don't know me. I'm a door gunner on a Huey. On May 19th, we took fire over the Ia Drang Valley. Bullet went through our fuel cell. I thought we were dead. But nothing happened. We flew home. My crew chief told me it was because of some foam you invented. I don't know if that's true. But if it is, thank you. I have a wife and a daughter. I get to see them again. Thank you. Specialist James Collier. Korkosz reads the letter 3 times. Folds it. Puts it in his desk drawer. He doesn't respond. Doesn't need to. The work speaks for itself. By September 1967, over 1,800 helicopters are retrofitted. The program expands to include CH-47 Chinooks, OH-6 Caillou Scouts, even some fixed-wing aircraft. The cost, $1.2 million. The return, immeasurable. But there's still one person who hasn't weighed in. One man whose opinion matters more than all the generals combined. General George S. Patton III, son of the legendary World War II commander. Commander of the 11th Armored Cavalry Regiment in Vietnam. He's been watching, testing, evaluating, and in October 1967, he's ready to make his decision. October 14, 1967. Long Binh Base, South Vietnam. 1,400 hours. General Patton stands beside a UH-1 Huey. The helicopter has been prepared specifically for this demonstration. 1 fuel tank filled with foam. 1 without. Patton requested this test personally. He doesn't trust reports. Doesn't trust data from stateside labs. He wants to see it himself. Under field conditions. Captain Korkosz flew in yesterday. He's standing 20 feet away, sweating in the Vietnamese heat. Nervous, Patton turns to him. Captain, you're telling me this foam works? Yes, sir. You're telling me it's been tested? Proven? Yes, sir. Patton nods. Then let's test it again. The demonstration begins. 2 fuel tanks are placed side by side on a clearing, both filled with JP4, both exposed, both identical except for the foam. A squad of soldiers sets up 50 meters away. M16 rifles. Tracer rounds loaded. Standard issue ammunition, Patton says. What our boys actually carry. Not laboratory conditions. Korkosz swallows. Understood, sir. Patton raises his hand. Tank 1. Fire. The squad opens up. 10 rifles. Full automatic. 30 seconds of sustained fire. The sound is deafening. Bullets tear through the aluminum. Holes perforate the tank. Fuel sprays. Then the tank explodes. The fireball rolls upward. Black smoke. Burning fuel splashes across the ground. The tank is destroyed, nothing left but shredded metal and flames. Patton watches. Expressionless. Tank 2. The foam-filled tank is positioned. Fire. The rifles open up again. Same ammunition. Same distance. Same rate of fire. Bullets punch through. Holes appear. Fuel leaks. But there's no explosion. The tank remains intact. Smoking. Punctured. But whole. Patton walks forward. Korkosz follows. They stop 10 feet from the tank. Fuel is dripping from a dozen holes. Inside, through the punctures, the foam is visible, blackened, smoldering, but solid. Patton reaches out. Touches the tank. Feels the heat. How many rounds did it take? He asks. Approximately 120, sir. And it didn't detonate? No, sir. Patton pulls his hand back. Looks at Korkosz. Why didn't we have this in World War II? The technology didn't exist, sir. Reticulated foam was only invented in 1956. The military application. I don't care about excuses, Patton interrupts. I care about results. He pauses. How many helicopters are retrofitted? 1,800, sir. Out of 2,400. How fast can we finish? By December, sir. Full fleet coverage. Patton nods. Make it November. Sir. November, Captain. Every helicopter. Every fuel tank. I don't care if you have to fly the foam in yourself. Yes, sir. Patton turns to his aide. Get me a line to MACV headquarters. He looks back at Korkosz. This foam, can it be used in ground vehicles? Korkosz blinks. Theoretically, yes. Tanks, APCs, fuel trucks, anything with a combustible fuel system. Then start testing it. I want proposals on my desk in 30 days. Yes, sir. Patton walks back toward his jeep. Then stops. Turns around. Captain, what's your background? Before the Air Force. Chemical engineering, sir. University of Illinois. Family. Wife and 2 sons, sir. Patton studies him for a moment. You know how many men you've saved? Korkosz hesitates. I've seen the estimates, sir. Approximately. Don't give me estimates. Give me honesty. How many men are alive today because of your foam? The question hangs in the air. Korkosz doesn't know how to answer. He's seen the reports, the after-action reviews, the letters from pilots. But he doesn't know. Can't know. I don't know, sir. Patton nods. Good answer. He steps closer. Lowers his voice. My father used to say that wars are won by logistics. By the men who solve problems no one else sees. You solved one. He extends his hand. Well done. Korkosz shakes it. Patton's grip is firm. Calloused. Thank you, sir. Patton releases his hand. Walks to the jeep. Climbs in. As the vehicle pulls away, Korkosz stands alone beside the punctured fuel tank. The foam inside is still smoldering. Still containing the combustion. He thinks about the letter from Specialist Collier, about the 58 helicopters that didn't explode, about the 240 lives, about the families, about the men who will never know how close they came to dying. In a single demonstration, everything changed. Not because of politics, not because of bureaucracy, because the foam worked. And now, it's official. By December 1967, every U.S. helicopter in Vietnam is retrofitted with reticulated polyurethane foam fuel tanks. The results are immediate. In 1966, fuel tank explosions accounted for 31% of all helicopter losses. In 1968, that number drops to 9%. The survival rate for crews involved in fuel tank hits increases from 12% to 68%. Over the next 5 years, from 1968 to 1973, the foam prevents an estimated 412 fuel tank explosions. That's 412 aircraft that should have been destroyed. At least 1,648 crew members who should have died. They didn't, because of the foam. But the impact doesn't stop in Vietnam. In 1970, the technology spreads to fixed-wing aircraft. A-1 Sky Raiders, F-4 Phantoms, C-130 cargo planes. Any aircraft with vulnerable fuel tanks gets foam. The cost per installation drops to $220 as production scales up. The weight decreases. The fuel capacity loss shrinks to less than 1%. By 1975, foam-filled fuel tanks are standard across the entire U.S. military aviation fleet. Over 12,000 aircraft. Every branch. Every mission type. The technology goes civilian. In 1978, the FAA recommends reticulated foam for commercial helicopters used in offshore oil operations. These aircraft fly low over water, operate in hazardous environments, face constant risk from mechanical failures and bird strikes. The foam gives them a safety margin, a buffer between a puncture and a catastrophe. By 1985, most commercial helicopter operators worldwide have adopted foam-filled tanks. The crash survival rate improves by 34%. In 1982, race car driver Gordon Smiley crashes at Indianapolis Motor Speedway. His fuel tank ruptures. The car explodes. He's killed instantly. Within 2 years, IndyCar mandates foam-filled fuel cells for all race vehicles. Formula One follows in 1984. NASCAR in 1987. The technology saves dozens of drivers' lives over the next 3 decades. Crashes that would have been fatal, fireball explosions, post-impact fires, become survivable. Drivers walk away because of the foam. In 1991, during the Gulf War, an UH-1 Apache helicopter takes fire over southern Iraq. Multiple hits. One round penetrates the forward fuel cell. The Apache doesn't explode. The pilot brings it back to base. Lands safely. A journalist photographs the helicopter. The image shows the bullet hole, the fuel stains, the intact structure. The caption reads, "How foam saved a $20 million aircraft." The photo goes viral. It appears in Aviation Week, in military journals, in engineering textbooks. It becomes the definitive proof. The visual evidence that a simple innovation, open-cell foam in a fuel tank, can mean the difference between life and death. By 2000, foam-filled fuel tanks are used in all U.S. military aircraft, most NATO aircraft, commercial helicopters, worldwide race cars across all major series armored vehicles, fuel transport trucks, even some speedboats and watercraft. The total number of explosions prevented, unknown. Estimates range from 5,000 to 15,000. The total number of lives saved, incalculable. In 2008, a CH-47 Chinook crashes in Afghanistan. The fuel tanks rupture. The foam prevents ignition. All 38 passengers survive. In 2012, an F-16 takes fire over Syria. Fuel cell punctured. Pilot ejects. Aircraft crashes. But the wreckage doesn't burn. The fuel doesn't detonate. Investigators recover the black box. The flight recorder. The evidence. The foam worked. Even in a crash. In 2015, a UH-60 Black Hawk goes down in Yemen. Direct hit from a rocket-propelled grenade. The fuel system is compromised. The helicopter crashes hard. The crew survives. All 4 of them. The after-action report credits the foam. Without fuel tank explosion suppression, crew survival probability, less than 5%. With foam, 87%. Veterans remember. In online forums. In reunion gatherings. In interviews for documentaries. They talk about close calls. About bullets passing through. About tracer rounds that should have killed them. We didn't think about the foam, one pilot says. It was just there. Part of the aircraft. But every time we took fire, every time we heard that ping of a round hitting the fuel tank, we thought, this is it. And then, nothing. We kept flying. Another pilot, I found out about the foam after my 3rd tour. Someone told me, you know there's foam in your fuel tanks, right? Stops explosions. I had no idea. I'd been flying for 2 years, and I didn't even know what was keeping me alive. A crew chief, we'd patch the holes. Drain the fuel. Pull out the foam. It would be scorched. Melted in places. But it did its job. We'd put in new foam. Refuel. Fly the next day. The innovation becomes invisible. Standard. Expected. Which is exactly what Korkosz wanted. He never sought recognition. Never gave interviews. Never wrote a memoir. He just wanted the aircraft to stop exploding. And they did. By 2020, over 50 years after the first installation, reticulated polyurethane foam has been used in over 100,000 aircraft worldwide. The manufacturing process has improved. The materials have evolved. Modern foam is lighter, more durable, more fire-resistant. But the principle remains the same. Break up the vapor. Prevent propagation. Stop the chain reaction. Simple. Elegant. Effective. And yet, almost no one knows the name behind it. Captain Robert H. Korkosz retired from the Air Force in 1979. Returned to civilian life. Worked as an engineering consultant. Raised his sons. Lived quietly in Ohio. He died in 2003. Age 76. Heart failure. His obituary mentioned his military service. His engineering career. His family. It didn't mention the foam. Didn't mention the lives saved. The explosions prevented. The legacy. But the pilots know. The crews know. The families know. And somewhere, in a drawer at Wright-Patterson Air Force Base, a letter still exists. Handwritten. Postmarked from Da Nang. 1967. I have a wife and a daughter. I get to see them again. Thank you. March 14, 1967. The day the Huey exploded at Tan Son Nhut. 6 soldiers killed. That crash is what drove Korkosz to make the final push. To demand the test. To force the demonstration. He couldn't save those 6 men. But he could save the next 6. And the 6 after that. In the end, the foam wasn't about chemistry. Wasn't about engineering. Wasn't about fuel vapors and combustion chains. It was about sending people home. Korkosz understood something fundamental. Innovation doesn't happen in laboratories. It happens when someone cares enough to refuse the acceptable answer. Helicopters explode when hit. That's just how it is. That was the acceptable answer. Korkosz rejected it. He found a solution in a hardware store. Tested it with kitchen sponges. Built proof from nothing but stubbornness and belief. And when the generals doubted, when the mechanics resisted, when the system pushed back, he didn't quit. He showed them the burning tank. The punctured holes. The intact structure. He showed them that simple could work. That lightweight could be strong. That ordinary materials could do extraordinary things. The foam wasn't revolutionary. It was practical. Unsexy. Boring, even. But it saved lives. Thousands of them. Today, every military helicopter in the U.S. fleet, every Black Hawk, every Apache, every Osprey, has foam-filled fuel tanks. So do most helicopters worldwide. So do race cars, transport vehicles, aircraft of every type. The technology that started with $400 and a kitchen sponge is now a multi-billion-dollar industry. But it began with one man, one test, one refusal to accept that soldiers had to die. Korkosz never wanted fame. He wanted results. He got them. His innovation is invisible now. Standard equipment. No one thinks about it. No one celebrates it. But every pilot who walks away from a crash, every crew that survives a fuel tank hit, every family that doesn't receive a folded flag, they're alive because of the foam. Because one engineer looked at a sponge and saw salvation. The story of the foam isn't just about technology. It's about what happens when someone refuses to accept tragedy as inevitable. When someone believes that problems have solutions, even if those solutions sound crazy. It's about the quiet heroes. The ones who don't make headlines, don't get medals, don't write books. They just do the work, solve the problem, save the lives, and then they go home. That's the legacy of Captain Robert H. Korkosz. Not a monument, not a parade, just aircraft that don't explode, just people who survive, just families who stay whole. If this story moved you, if you learned something, felt something, take a moment to hit that like button. Share where you're watching from in the comments. You're not just engaging with a video. You're keeping these stories alive. You're making sure that the quiet heroes, the engineers, the innovators, the problem solvers, aren't forgotten. History isn't just about battles and generals. It's about people who saw a problem and refused to walk away. People like Korkosz. People who changed the world with foam. In the end, the greatest innovations aren't always loud. Sometimes they're just a whisper, a small idea that refuses to burn out.